Yay. Okay. Good morning, everyone. This is week 8, our studio workshop for you guys. The last week, we learned how to program in R using some basic syntax. If you still remember, we talked about the data structure, the decision making statements, if, else, something like that. And then also talk about looping, okay, the repeat, while loop, for loop. Okay. Today, we're going to cover an important topic. It's called the recursion. Okay, and then we'll probably briefly talk about debugging in R. Okay, so that's today's topics, recursion and debugging. Now, have you heard about the word recursion or recursive? If you Google the meaning of this word in English, it says something occurs when a thing is defined in terms of itself. In computer programming, recursive function is very, very powerful because many things can be done through a recursive function. So again, if a function is recursive, that means the function is working, doing something, or calling himself to do the job. Okay, so let's have a look at example, mathematical example today, and then try to code this thing in R. The math example I'd like to talk about is called Fibonacci sequence of numbers. Fibonacci sequence of numbers or Fibonacci numbers. The sequence is defined like this. The first two items are 0 and 1, right? Very simple numbers, 0 and 1. And the following numbers is just the sum of the previous two numbers. So the first number is 0, second number is 1, and the third number will be 0 plus 1, which is 1. And the fourth number will be the sum of the previous two, which is 1 plus 1, get 2. And the next one will be 1 plus 2, you get 3. And then keep going. The Fibonacci sequence is going on forever, all right? Yeah. So I just list the first 10 items here. And the first 12 items here. So you can see this is an example of Fibonacci example of recursive function. This one, Fn is equal to Fn minus 1 plus Fn minus 2. So the current number or item in the sequence is equal to the sum of the previous two items. Okay. So if I want to calculate Fibonacci number, let's say Fn F5, that will be equal to F4 plus F3. And then we have to figure out, okay, how to calculate F3 and F4. We'll come back to use the same function. So F3 is equal to F2 plus F1. F4 is equal to F2 plus F3. And then, keep using the same function, using itself to figure out the result. Yeah, this is kind of example of a recursive function or recursion mathematically. Okay. Yeah. Fibonacci sequence is very famous because many things in the nature have can be related to Fibonacci sequence of numbers. And an important thing of Fibonacci sequence of numbers is that if you divide the immediate, the neighboring two items, their ratio is approaching something we call golden ratio. Okay, so if you divide Fn plus 1 over Fn, as n goes to infinity, that ratio will approach very, very closely to the golden ratio. As we know, we know that the golden ratio is equal to 1 plus the square root of 5 over 2. It's about 1.618033, blah, blah, blah. It's an irrational number, so it's never ending. Okay, yeah. So the ratio of neighboring two items in Fibonacci sequence is approaching the golden ratio as the sequence grows to infinity. Okay. So how can I use R language to generate a Fibonacci sequence? Okay, and then we can use our R function about Fibonacci sequence to calculate or approximate the golden ratio. Okay, let's try that today. So we're going to create a function in R to generate Fibonacci sequence. And then this function is going to be recursive. Okay, so if you like, you can follow me in RStudio to try this task. So I'm going to call my recursive function to create or generate Fibonacci sequence. I call it recurse underscore Fibonacci. Just the name of the function I like to call it. You can name it whatever you like. Okay, yeah. So I call this one recurse underscore Fibonacci. Okay, that's the name of the function. And then I'm going to define this function. So of course, I have to tell R it's going to be a function. Okay. And what I want to do is I want to make this function to return the term in the Fibonacci sequence if I tell the function the position of the term. So the input will be the position of the term, which is n, and then output will be the number of that term. So if you look at the mathematical definition here, conventionally we start the indexing from 0. So the first term is called F0. Okay. Second term is called F1. The first term is 0, so F0, 0. Second term is F1, which is 1. And then the next term will be Fm equal to Fn minus 1 plus Fn minus 2, where the n has to be larger than 1. And of course, n is a natural number, okay, counting number, like a 1, 2, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, blah, blah. Okay. Okay. So my function will calculate the n plus 1's term of Fibonacci sequence. Okay. So if n is 0, a function will return the first term. If n is 1, a function will return the second term, right? And then if by n is 2, that will be f2. That's the third term. Okay, just make it consistent with my mathematical notation on the previous page. Okay, so n is 0, 1, 2, 3, 4, 5, 6, blah blah blah. Okay. Okay. Any question?
No.
No, all good, all good. Yeah, yeah. It's a bit tricky. So I don't know. So we're trying to create a function that is kind of matching our mathematical notation on this page. Okay, so f0 is first term, f1 second term, fn is n plus 1's term. So f2 will be the third term. f2 will be the third term. Okay, yeah. So again here, we'll calculate the n plus 1's term of the sequence. All right, so the input is just the number, the sequence, the position index, n. Okay, so this is how I construct this function. So we know that if n is equal or less than 1, let's say 0 or 1, I should just return 0 or 1, right? The first two items of Fibonacci sequence. So if n is 0, fn is 0. If n is 1, f1 is 1, right? And then when n is 2 or larger, the fn will be fn minus 1 plus fn minus 2. So if n is 2, the f2 will be f1 plus f0, which is 1 plus 0, which is 1. Okay, yeah. So here I say we can use the stuff we learned last week, the decision-making statement, if else. So if n is equal or less than 1, that's the logical evaluation in R. If equal or less than 1, then we just return the n according to the definition of Fibonacci sequence. Else, otherwise, so that means if n is larger than 1, that means 2 or 3 or blah, blah, blah. The larger natural numbers, okay? We will going to do this part. So this is the tricky part. This is the recursive part. We're going to return fn minus 1 plus fn minus 2. And then fn minus 1 comes from, we just reuse our function recursive Fibonacci. fn minus 1 plus fn minus 2. Can you see the mapping between this R code and here, the mathematical definition?
Yep.
Yep. Yeah. Yeah. So that's the magical part, recursive part, or recursion, where the recursion happens. Okay. So we just run manually. If n is 0, then because 0 is less than 1, so return value of n, which is 0. That's good. The fn is 0, which is correct. If n is 1, okay, is equal or less than 1, so return 1, which is also correct according to our definition here. And if n is 2, the if part, if n minus equal less than 1, okay, it's not. So if we go to the else part, so return recursive Fibonacci function n minus 1. So remember now n is 2, so this one will calculate recursive Fibonacci 1, which we know will return, we get 1 from here. Plus recursive Fibonacci n minus 2, n is 2, so 2 minus 2 is 0. So we can calculate the Fibonacci return recursive Fibonacci 0, which will get 0 from here. Okay, so when n is 2, we will get 1 plus 0, which is 1. Good. That's F2. F2 should be 1. Okay. And then we keep going. So if n is 3, the function will calculate the fourth term. If n is 3, F3 is equal to, we come back to else again, recursive Fibonacci 2 plus recursive Fibonacci 1. And then recursive Fibonacci 2 will reuse this function itself to figure out that is 1. And then recursive Fibonacci n is 3. So Fibonacci 1, that is also 1. Okay. So F3 will be equal to 2. Okay. Yeah, that's it should be working, okay? And if we can test it, it must be working, okay? Let's go to my R. So let's define this function. See, so let's define this function. Okay. That's how I define this function. Run. Function is defined. It looks okay, and then we can try. Let's say we want F5. Okay, let's say we try F5. Calculate F5. Okay, let's make some personal note. So F5 should be equal to recur. Yeah, I got a hint. That means my function was defined properly. So F5 should be equal to 5, right? Let's put a 5 here. So recursive Fibonacci 5, that will calculate F5 of this Fibonacci sequence. That is the n plus 1's term, the 6th term. And according to our definition, it should be equal to F0, F1, F2, F3, F4, F5. So F5 should be equal to 5. Okay, let's run this one. If we get a 5 in the console or not. Hopefully, it gets 5. Yahoo! It's 5. We'll try again. F6, F7, F8, F9, F10, F11. Let's try F11. That's the 12th term. Should be 89. So if I try F11, Control Enter, 89. All right. So I'm pretty sure my function is correct. You can give a try. You can give a try if you like. Yeah, give a try if you like. So after creating and validating my Fibonacci item or term generation function, I call this one recursive Fibonacci. I'm going to use this function to create a Fibonacci sequence, so multiple numbers in this sequence. Okay. So this is the right hand side of this slide here. So basically, I can request a number of terms, a sequence of n terms in the Fibonacci sequence. So number of terms I'm going to save in this object called the n terms. For example, I can request the first 10 terms. Okay, so I should write this one first. First 10 terms. So my n terms will be equal to 10. And I'm going to use this loop to to use my recurse Fibonacci function n times and to print out the first 10 terms of the Fibonacci sequence. So this is my coding. So first of all, I'm going to check if n term is a valid number, because it has to be positive integer. Okay, it has to be a positive integer. Okay, n terms. We have to request. You can't request -5 terms. It has to be like a 1 or 2 or 3, 4, 5, or 100, whatever, a positive integer. Okay. And if the n term is not a positive integer, I'm going to give this reminder. So please assign a positive integer to n terms. Okay. So how do I check it? I check here. So if n terms is less or equal to 0, or is all, or n terms is not an integer. Okay. So how do I check if n terms is integer or not? I just divide it by 1, and then check the remainder, the modulus, after dividing by 1. If the modulus is 0, then it is an integer. If the modulus is not a 0, then the n term is not an integer. Like if I put a 3.5 divided by 1, the remainder is 0.5. It's not 0, so it's not an integer. Okay, so this I'm checking if n is not a positive integer. Okay. If that's true, I'm going to print this warning, and then doing nothing else. Okay, and if n term is a positive integer, that means not less or equal to 0, or a decimal number. That means a positive integer. I'm going to do the else. Okay. Define my code here. Hold on. Define my slide here. Oh, what happened? Positive integer. Okay. So if n is a positive integer, that means 1 or 2 or 3 or 4 or 5 or whatever. Large counting number. I'm going to reuse my recursive Fibonacci function multiple times. Each time print out a Fibonacci number. So I'm going to use the for loop for every term for every I in this sequence. This is a sequence. Can you see that? This is a sequence. Remember last week I said when we know when we have a sequence or vector of things, and then we want to loop through every single item in the sequence or vector. Normally we're going to use a for loop, a for loop, right? Yeah. So now I have a input of n terms. Just the user want to request the first n terms of Fibonacci sequence. So I'm going to use for loop to generate the n terms of first n terms of Fibonacci sequence. Remember our indexing number of Fibonacci sequence of our function is starting from 0, just like the mathematical definition here. Okay, So my sequence number also starting from 0 until n terms minus 1. So if n terms 10, I want to request the first 10 terms of Fibonacci sequence. I'm going to calculate F0, F1, F2, F3, all the way up to F9. And that's the first 10 terms of Fibonacci sequence. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the first n terms. Okay. Yeah. And then after figuring out the index, I just have to print recursive Fibonacci I. The first one will be recursive Fibonacci 0. And then recursive Fibonacci 1, recursive Fibonacci 2, all the way up to the last item, which is recursive Fibonacci n terms minus 1. So if n terms 10, the last number to print out to calculate is with recursive Fibonacci 9. That's F9, right? F9 is the 10th term. Okay. Okay. And after doing that, I will print out this sentence. The first items of Fibonacci sequence have been calculated. Sorry, this I is not this I, okay? This I is just to replace percentage I, this part, with this value, n terms. So if n terms 10, this one will say the first 10 terms of Fibonacci sequence will be calculated as printf. This is how we insert this part as a variable from the value of these n terms. All right, the best way to do is just give a check. Give a check. So I'm going to define this n term. Just copy the whole thing. C. Go to my R. Okay. Ooh, that's a bit large. So where did I start here? So first of all, I'm going to define my n terms as 10. I'm going to request the first 10 terms, and then I will run this. So I hope I will see 10 numbers. It should be F1, F0, F1, F2, all the way up to F9. And then a sentence at the bottom. The first 10 terms of Fibonacci sequence have been calculated. Okay, let's try it. Run. Did it run? Oh yeah, yes, it run in the console. All right. Okay. You can give a try, so if you can get the same result. Zero, 1, 1, 2, 3, 4, 5, 8, 13. That's the first 10 terms. Yeah. Did it work on you, on your computer?
Yes.
Yes. Lucky. Lucky. Yes, it's yeah, calculate the n plus 1 term. Should see here. And is equal to 0, 1. Mm. Okay. Yeah. Oops. Sorry. The light in the room become dark. Doesn't matter. All right. N is the same as my annotation on the previous page. Okay, cool. All right, next page. Almost done. We're almost done. All right. So next one, we're going to approximate the value of golden ratio using our Fibonacci sequence generation function, which is coded in R. So we need the two vectors. So one vector is to save the Fibonacci sequence numbers, and the other vector is to save the the calculation of the ratio of the neighboring two Fibonacci numbers, and we're going to see if that ratio of the neighboring two Fibonacci numbers is going to approach the value of golden ratio. Okay, we know that golden ratio is equal to this number. We call it phi conventionally. Is equal to 1 plus square root of 5, and then the thing divided by 2 is about approximately 1.618. Okay. So again, I'm going to use the for loop again. And also if else statement to make decision. And then we're going to also use the break statement here. Yeah. Remember break statement in the loop? That means break the loop, jump out of the whole the current loop. Okay. Yeah. So again, if we request the first n terms, we're going to use the recursive Fibonacci function we defined before to calculate the n terms one by one. So it's f0 to fn minus 1. So if n is 10, we're going to calculate f0, f1 all the way up to f9, the first 10 terms of Fibonacci sequence. Okay. So how do we do that? we're going to use this C function to create our vector. Our original, the Fibonacci sequence vector FIB is empty. See, nothing in the C function here. C empty pair of brackets. And then every time in the loop, we're going to add one more item to the end of this FIB vector. Okay, which is the C function. Okay, for the for loop. The first one will be FIB will be Fibonacci sequence number F0, and then add one more F1, F2, blah blah blah. Okay. If the n terms is 3, if we just calculate, if the n term is less than 3, so if we just request 1 or 2 terms of Fibonacci sequence, we can't calculate that ratio. Okay. If we just request 1 term as F0, there's no ratio to calculate. If we request 2 terms, we get F0 and F1. We still cannot calculate the ratio because the ratio will be 1/0. That's undefined. So we have to request at least three terms. So n terms have to be 3 or larger. Okay. So we can only start calculating ratio from the 3rd term. So n term has to be 3 or larger. Okay. So if our n term is 3 or larger, we don't have to, we will not do this, we will not break, we will go to else. Okay, if our n term is 3 or larger, we will come to else. We will be calculate the ratios for the neighboring two Fibonacci sequence items. Okay. So remember our looping of I starting from 0. When I is 0, there's no ratio to calculate. When I is 1, the ratio cannot be calculated because the first term is 0. So here, when I is less than 2, that means when I is 0, 1, we do nothing. We do next. Remember the next statement we learned last week? The break statement is to break the loop. The next statement is to skip the current round and then move to next round of the loop. Okay. Yeah.
Sorry, I just have to leave for now.
Yeah.
Thank you so
All
much.
right. No problem. Get try later.
Bye.
Right. So if I is 2 or larger, ratio can be calculated as fib I plus 1 over fi fib I. Okay. Yeah. So we can give a try of this part. Go back to R. So first of all, let's define these two empty vectors. Empty. Okay, and then our n term is still 0, so it should be fine. So we will start from 0 until 9. Okay, because our n term is not less than 3, so we come back to it. This one. Yeah. And then initially I is 0, so we do next. Next. Okay, we now move to 1, and then 1 we calculate Fibonacci sequence F1 and add up to the FIB vector, and then again we come back to here. Again, 1 is still less than 2. We do next. So when I is 2, that's the third term. We calculate F2 and add it up to the Fibonacci sequence, FIB. And then again, the n term is 10, is not less than 3. We come back to else here. And then now if our I is 2, we're not going to move to the next round. We're going to do the else here. So the ratio will be equal to the ratio will be equal to F Fibonacci 3 over F Fibonacci 2. Let's see if it's working. Yeah, it worked. So we get these two vectors. That's the first 10 terms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the first 10 terms of Fibonacci sequence, and then ratio vector. Let's look at this. 1, 2, 3, 4, 5, 6, 7, 8. 8 ratios. Okay, the first one comes from third term over second term, and then second one, third ratio, fourth, fifth, seventh, eighth. Have 8 ratios, right? Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 8 ratios. 1, 2, 3, 8 ratios. Yeah, it works. And the last part here is just to I just try to a chart, a run chart, to visualize the summation of the ratio to the golden ratio. So that's stuff we learned in the previous weeks about ggplot. Okay, yeah. So I just created data frame. It's called has 2 columns. The first column is the term position, starting from the third term. Okay. The ratio can only be calculated when Fn is 2, okay, or larger. Yeah, starting from the third term. And the second column is vector of ratio. Okay, so n is from 3 to n terms. is the data frame, 2 vectors. And then the golden ratio, the true value is n is 1 plus square root of 5 divided by 2. Okay, so I'm using ggplot2. So I'm going to plot the data. The horizontal axis is the n, the position, third term and until the n term. And the geometry is line to show the value of ratio. I have a horizontal reference line of the ratio is dashed, is red. Backgrounds are black and white, and then label the horizontal and the vertical axis. By this, going to define a sequence of positions from 3 to n. Make a data frame. Data. Have a look. This is the data. 2 columns, 8 observations. Third term, fourth term, fifth term, all the way up to 10th term, n term. And then the corresponding calculation of the ratio of the current term over the previous term. And then once I have the ratio, we can use plot, calculate the golden ratio is 1.618, blah, blah, blah. And then load the ggplot2, and then we can put this chart. There you go. We get this chart. You can see the true value is a red line, red dashed line, and then the ratio jump up and down as n goes to larger and larger. This ratio of neighboring two sequence is kind of approaching very quickly, approaching the true golden ratio value, which is 1.618, blah, blah, blah. Yeah. Okay. That's basically the thing for today. Yeah. Any questions? All right. And next one, we'll just briefly talk about the debugging of our code. So first of all, there's a one page we probably have to read. So we need to know the environment hierarchy and the scoping rules of please be patient, just read through this page. So we just say every file on your computer is saved in a folder, and each folder is saved in another folder. So this way the files will form a hierarchical file system. Okay? So we know that we have folders and we have folders in folders. So if your computer wants to open up a file, it must first look up the file in the file system. So R use a similar system to save R objects. Okay, we have lots of R objects. You can see in the environment here, we have objects. Each object is saved inside an environment, which is a list-like object that resembles a folder on your computer. Okay. And each environment is connected to a parent environment. So if you know the folder system, folder in folders, you can think of, R is using the same kind of hierarchical system to locate objects. So we have them saved in environments, and then have environments within environments. So each environment has a parent environment, or higher level environment. So we have a hierarchical environment system, okay, just like the hierarchical file system, folder system. However, in R, there's no way to look at one environment and tell what is its parent. Children. So you can only search up, but not search down as environment tree. So basically, if I know an environment in R, I can only know its parent environment, and then parent's parent. I can search up the environment tree, but I cannot search down the environment tree because given the environment, the system cannot tell us who are these current environments, children environments. It's just, I don't know, just define, just create it like that. So at any moment of time, I is working closely with a single environment. And I will store new objects in this environment if you create any. Okay. And I will use this current environment as a starting point to look up existing objects if you call any. So if you have in your function or in your syntax, if you are using any object, the R will search that object in the currently working environment. Okay. We call this one active environment, currently active environment. And if I cannot find it, what will it do? I will follow a special set of rules we call it scoping rules to look up the objects you are calling. Okay, so I will look for the objects in the current active environment. When the R cannot find the object you are looking for, I will look up the environment tree. So we'll look for the object in the current environment's parent environment. And then still cannot find it, we could look up the parent's environment, and so on, until I find the objects, or until we reach the empty environment, which is top. And then if I still cannot find it, it will return an error message saying that the object is not found. Okay, that's the hierarchical environment tree and also the scoping. Yeah, it just working like that in our language. This one. Active environment. Yeah. Okay. And then errors and debugging. as we write complex codes, we may get an error or a result different from our expectation. So there are basically three types of uh, um, errors. Syntax error are basically the typos in our syntax, like you know, if you type the wrong name of object or function name, missing half of the pair of parentheses. Okay. So RStudio will highlight the syntax error with a red squiggle line. This syntax error is easy, probably the easiest one to fix. The second type is a runtime error, which occurs for example, we have a loop and then we don't have a there's no ending condition for the loop. That means the loop will running. That will be a runtime error. And the last one is logical error, which is the hardest one to find. So you write the code, there's no syntax message, and you run, it finished, and then but the result is it is not the result is not the result which we expected, or we want the code to return. Yeah, and this type of error sometimes is hard to notice. Yeah, so it's logical error. So there's basically three types of errors. So for example, when we have a functions within functions within functions, also multiple layers of functions and the looping, so things can be complicated. We can use some debugging tools to help us step in function and the function of function, and then to trace the code step by step, and then hopefully we can find the source of the problem. That's the bug. We can also use debugging to check the functions of the R packages if you like. So if we are doing coding, the language will have to be kind of get used to debugging, because it's part of of a real coder's everyday life. Nobody can guarantee a code without any bugs. So it's always good to think through before you start typing your code. So the aim of debugging is to figure out where and why, and then fix it. Okay. So they are the commonly used tools. Breakpoints allow you to put a point in your code, in your syntax, and then R will, when you run the code, R will there, and then you can kind of pause the code at the breakpoints, and then you can check. It's a feature in RStudio. And a few functions we can use: trace back, browser, debug, and undebug. So I found two videos on YouTube. The video is still available. I checked the other day. I'm not going to demonstrate how to use them. So if you are interested in this topic, you can have a watch of these two videos. They demonstrated how to use this four tools in a piece of R code. One is in the traditional R interface. The other one is in the RStudio environment. Yeah. They're both about 10 minutes long, more or less. Yeah. Okay. That's the end for this topic for this week, and also wrapping up the basics of programming R in this week and then last week together. Next time we will come back to our usual topics of probability and statistical data analysis using RStudio. So next time we'll talk about the probability functions and how to use them in R language. Yeah. Okay, thank you very much. Bye-bye.